Another big problem that students have when it comes to determining the scattering matrix or scattering parameters of some circuit is that first step where we have to apply the scattering parameter experiment to the schematic. We just can't look at a schematic and immediately begin to analyze. We have to set up the experiment for each column of the scattering matrix, and that involves going through and making sure that there is an incident wave on one port, but one port only. Oftentimes we put matched loads on, schematically speaking, on the other ports, or we simply can enforce that condition when we write down the telegrapher equations, making the incident waves on the other ports equal to 0 as a first step knowledge going forward before applying boundary conditions, for example. So getting that experiment set up correctly is very important to getting the right answer. We've done this before in impedance matrix, for example. One of the things that we did that made it a little bit easier for an impedance matrix was just go ahead and set up a current source, an ideal current source on one port and one port only. To make sure the other ports were equal to 0 current, we went through and we applied open circuits there. Again, we could look at this as applying current sources at every port. One of the ports, the current source is non-zero. All of the other ports, the current source is equal to 0. I is equal to 0 is an open circuit. But this was a way to set up the circuit to apply the experiment to determine the first column of the impedance matrix. And once we determine V1 and V2 for this current, then we could determine for, in this case, Z11, Z21, and then we turn this current off, make it 0, make it an open circuit, turn this current source on, make it non-zero, and then go through and find the second column by finding the resulting voltages in V1 and V2 with the non-zero current over there. So that was the process that we went through, and that's the process of turning sources on and turning sources off and putting them in the right ports that was crucial to getting the right answer. So for admittance parameters, the admittance matrix, we had a similar thing. We could go through and apply a voltage source essentially at all ports, set the voltage sources at all ports but one equal to 0, only having one port where we had a non-zero voltage source. And then we calculated the currents at flowing into each port, and from that we could determine the transadmittance parameters, in this case for that first column, Y11 and Y21. And then we would turn this voltage source off, set it to 0, making it a short circuit, turn this voltage source back on to non-zero value, and then reanalyzing I1 and I2, which allowed us to get the second column. So this was, again, the set of experiments that we set up to determine each column of the admittance matrix. And again, that was a very important step to make sure we understood how to set up those experiments and go through them to get our answers. Now, what about scattering parameters? Is there a similar thing that we can do here? Similar sources that we could connect somehow to our network, which allow us would properly set up the experiment that we want. So this is a useful way of setting up the experiment, the schematic that we need to analyze, so to be able to find the scattering parameters. In this case, we're going to have an incident wave on port 1. And of course, we can simply, in our telegrapher equations, just say V0 plus, V01 plus rather, is non-zero. Just make it a non-zero value. And then we'd have some incident wave. But we're going to go through and assume that we have generated an incident wave by placing a matched source onto our transmission line. So notice the source impedance here is Z0. Now, notice what happened to the transmission lines. Well, we're going to put the matched source at the very beginning of our transmission line out here, but remember, when we have a matched source and we have a length of transmission line, that is a source transformer, and that transforms the source into a new source, which has exactly the same characteristic, same output impedance of Z0. So we can think of this as two steps. We put a matched source at the end of our transmission line, and then we came up with the equivalent circuit looking back here. So this is the equivalent circuit of a length of transmission line with a matched source on the end, and of course that simply is a matched source. This is what's generating the energy that is going into our device. On the other side, we will go through and take a length of the transmission line, and we can put a matched load at the end. And of course, that will ensure that there is no incident wave coming down on port 2. But we again can simply replace that structure with its equivalent circuit. We know the input impedance of any transmission line terminated in a matched load will be equal to that characteristic impedance, Z0. So we're going to replace the length of transmission line terminated with Z0 by simply a load numerically equal to 0, 0. We're going to put this onto port 2. Again, we don't have to do it this way, but this is a way of setting up the experiment, which actually makes things a little bit easier, as we'll see, for in many cases, for the analysis here. So again, we could write the telegrapher equations and just say V0 plus, V01 plus is non-zero and V02 plus is equal to 0, and then apply boundary conditions. That's fine. There's nothing wrong with that. Or we could set up the experiment this way, where we have a matched source on one port and matched loads directly connected to all the other. And again, this is reminiscent of what we did for impedance and admittance matrix, where we put an ideal voltage or current source on one port and one port only, and then put short circuits or open circuits on all the other ports. In this case, we're putting one matched source on one port and one port only, and then the other ports we attached matched loads. From this, we can determine the scatter. By analysis of this structure, we can determine the scattering parameters. One nice thing about this particular problem, you look at it, it looks like a freshman circuits problem, doesn't it? I mean, it's just lumped impedances, and we can go through and find the total voltage V1 here and V2 here. This is the port voltage V1 and V2. So the real trick here is to try to parse out the incident and scattered waves from the total voltage. V1 is the sum of both the incident and scattered wave from port 1, and likewise for port 2. So that's the only little thing we have to work on, but it turns out not to be particularly difficult. So again, that previous schematic where we put a matched load and a matched source on the device sort of reduced it to looking like a freshman circuits problem. We don't see transmission lines anywhere. Now remember, they're still there. We just replace them with the equivalent circuits for the matched source and the matched load. We go through and do the analysis, and again, what we find is the port voltage V1, port voltage V2. This is the total voltage, the sum of the incident and reflected wave. Moreover, we'll find that these voltages are going to be in terms of the value VG, which is the open circuit voltage for that matched source. We know the source impedance is Z0. VG is just a value there. We leave that as a variable. It turns out it doesn't matter. We can get the scattering parameters. It'll cancel out, and the value doesn't matter. There. So the question is, how do we do that? How do we go through and extract the incident and scattered wave values from these total voltage values, particularly since they are in terms of VG? Well, let's first look at the ports that are terminated in matched loads. Of course, for these ports, there is no incident wave. If we've terminated our transmission line in a matched load, then we know there is no plus wave that can come from that passive matched load. And so we know for all the ports that are, again, terminated in matched loads that this is the case. The plus wave is equal to 0. Now, remember, the total voltage is simply the sum of the plus wave voltage and the minus wave voltage, the incident voltage and the scattered voltage. If the incident voltage is equal to 0, then the total voltage is just the scattered voltage. The scattered voltage is the total voltage, the port voltage. And so we can write it down mathematically. The scattered voltage, the minus wave voltage, is the total voltage minus the incident wave voltage. But the incident wave voltage for these terminated ports, terminated matched loads, is equal to 0, and therefore we find the total voltage at those ports is precisely equal to the scattered voltage at those ports, the minus wave voltage. Again, the plus wave voltage is 0, so the two are equivalent. So finding the total voltage at some port that's terminated in a matched load is, in fact, exactly the same as determining the scattered wave, which is what we're trying to find to determine our scattering parameters. The bigger problem then becomes when we're trying to find what is the scattered wave, the exiting wave, at the port where the incident wave is non-zero, the port where we have not attached a matched load, but instead have attached a matched source. So now the exiting wave from that port, where we have the matched source, we know is the total voltage minus the incident voltage. But now this incident voltage, this plus voltage, is not equal to 0. And therefore the minus wave voltage at these ports with the match source is not going to be equal to the total voltage. So how do we determine the scattered voltage for this case? How do we take the total voltage and essentially parse it into two pieces? One part which is the exiting or scattered wave, and the other part which is the incident wave, the plus wave. How do we determine this value? Well, to do that, we need to figure out what is the value of the incident wave. What is the plus voltage at the port plane when we attach a match source to it? And this is why we attached a match source as opposed to any other source. I could have put a source there with an output impedance of any arbitrary value. Heck, it could have been a reactive output impedance. It would generate an incident wave, and from that we could determine then the scattering parameters. But it would have taken us a lot of time, because we would take a lot of time to figure out what is the value of the incident wave that is striking that port. We picked specifically a match source because it allowed us to determine this value very quickly. So you recall, I hope you recall, that we studied this special case. What happens when we attach a match source to a transmission line? Didn't say anything about what was terminated at the other end. We just looked at the interface of that source connected to the transmission line if the source impedance was numerically equal to Z0. And there were a lot of things that simplified very nicely in that case. And there was one I tried to emphasize. I said, put in your microwave load. Remember this. This is going to be important later. And that fact was that for a match source, the value of the plus wave, the value of the incident wave, or exiting that source, the value of that plus wave at the source port is going to be Vg over 2, Vg being the open circuit voltage of that match source. And this is true regardless of what that source is ultimately connected to. If that source has a source impedance numerically equal to Z0, then this statement is true. But of course, this is exactly what we need to know if we are to determine the exiting wave from that port in our scattering parameter analysis. On the previous page, we said the exiting wave at a port where a match load, or match source rather, is attached is equal to the total voltage at that point minus the incident wave voltage, the plus wave voltage at that port plane. Well, if we've attached a match source to that port plane, we know that incident voltage is Vg over 2. And so now we can come up with this very exciting, simple, easy result. The wave voltage exiting that port where the match source is attached is equal to the total voltage, which we've determined by analysis, minus 1/2 Vg. So we do the analysis using our freshman circuits, and we get a total port voltage at some port where the match source is connected there, 6 volts or whatever, and then 6 volts complex, of course, and then we subtract from that 1/2 Vg. And that gives us the value of the exiting wave, and that's what we need to determine scattering parameters. So now we have a method of determining the scattering parameters from a circuit by attaching one match source and then the remainder ports of match loads, and doing an analysis to find the total voltage at each of the ports. And this will allow us to determine one column of our scattering matrix, whatever column is associated with the port that the match source is attached to there. And so let's see what the mathematics would be for this. We can write our scattering parameter for an off-diagonal element. This is for an element Mn, where Mn is not equal to N. And so in this case, the exiting wave is a wave for a port that is attached to a matched load. There's no incident wave for that port. N is the port where we do have an incident wave. And again, M and N are different values for this off-diagonal element of the scattering parameter. So S21, S34, S14, whatever. That's what we're talking about here, an off-diagonal element. So we can take the definition and write it in this form. Again, we just took the normalized wave amplitudes and did a little algebra and showed that this is the scattering parameter result that we get. And we wrote in this way so we could go look at these two values. First of all, what is the exiting wave on port M? Well, because we have a matched load we know that the exiting wave at port M is simply equal to the total voltage at port M. What about the incident wave at port N? Again, this is the important part, the thing that really is slick about using a matched source to excite the incident wave. We know the value of the incident wave at that port plane since we attached the source right there. That value is 1/2 VG. And so we find that we can write the scattering parameter for the off-diagonal elements in this form. We go through and S21, we take 2 times the total voltage, the port voltage at port 2, for example, and then divide by VG, and then multiply it by the ratio of the square root of the proper characteristic impedance. Now, be careful right here, all right, the ratio of these characteristic impedances. Notice we have Vm minus over Vn plus. Vm is in the numerator and Vn is in the denominator. But that's opposite of what we have in the characteristic impedance here, right? This is Z0n, which is associated with the incident wave, and this is Z0m, which is the transmission line where we have the exiting or scattered wave at port M. So sometimes students will get these inverted. They'll put, if there's an M here, there should be an M here. Well, no, that's an N. If there's N's here, there should be an N here. Well, no, that's an M. So be careful there. All right, what about the diagonal elements? We go through and take our scattering parameter definition with our normalized wave amplitudes, and we can write the scattering parameter for a diagonal element, and in this case n is equal to n, so this will be S11, S22, S33. There we write it in this form. Now in this case the square roots of the characteristic impedance will cancel each other out, because we're talking about the exiting wave on port N, the scattered wave on port N, and the incident wave on that same port N. So the incident and exiting wave for that port are going to, of course, have the same characteristic impedance because they're on the same transmission line. So this will always cancel out. Again, it doesn't cancel out here because M and N are different, but it does cancel here because N is equal to N. These are both the same values. They cancel out. What about V minus? V minus is different, of course, than what we had up here on the off-diagonal elements. V minus, the scattered wave for the port where the matched source is attached, we know is the total voltage for that port, and that's what you found from analysis. You're going to find this total voltage, and we're going to put it right in there, and then subtract from that 1/2 VG. That's the value of the incident wave on that port, and then divide it by 1/2 VG, because once again that is the value of the incident wave at that port. So this is the exiting wave at the port where the matched source is attached. This is the incident wave at that same port. We can do a little algebra and rearrange it in this way. Now, you look at this and it seems like the VGs are not going to cancel out, but they will, because the total voltage that we got at port N will be a function of that VG. Ultimately, that's the source that's causing the excitation. So all of our port voltages will be in terms of VG, and when you do the analysis, VG will cancel out and disappear, as it must. Remember, the scattering parameter can depend on the device parameters and the characteristic impedance of the transmission line, and them only. So if you have VG lurking somewhere in your result for the scattering parameter, then you've done something wrong. Go through and figure out how it cancels out, as it must, and if you can't figure out how it cancels out, you've done something wrong in your analysis. So that's a good sandy check. Make sure your VGs cancel out. So this is a summary of what we said here, some box you can kind of look at to use these equations. And again, at this point, when we have the answer, there's really not too much physical insight. This is sort of a recipe that you want to write down and probably memorize. Figure out where it comes from, understand why this works, but in the end, this is kind of a plug and chug equation for this technique. For the one port where there's a matched source, and there can only be one port with a matched source for each column. Again, it changes for each column. The port with a matched source, we'll call it N. The incident wave voltage at that port plane must be VG over 2 from the special case, and therefore the exiting wave at that same port, the port N with the matched source, is simply the total voltage that you calculate minus VG over 2. For the remaining imports with match loads, then we find that the incident wave, of course, is 0 since we have match loads there. The scattered waves, therefore, are simply equal to the total voltages that you calculate for those ports. And again, this will be in terms of the source open circuit match source voltage VG when you do your analysis. And then because of that, these two statements, the diagonal elements of the scattering matrix can be found in this form, and the off-diagonal elements can be found in this form. And again, you simply insert there. The VG show up, but the answers for Vn and Vm better be in terms of VG, in fact, proportional, so that they will cancel out, and you'll get an answer independent of VG. Again, if it doesn't, you've done something incorrect. Now, remember, this is just for one column. We put the incident, the match source on port 1, and then it allows us to find the first column of the scattering matrix. And then we have to do another analysis, another experiment. We move the match source to port 2, and then put a match load on port 1, and then calculate the circuit for that and find all the values exiting, and from that we get the second column, and then we move to the third, and so on. One thing to bear in mind, one thing you should keep in mind when you look at your circuit, though, is what symmetry is there. Do I really need to go and evaluate all these scattering parameters, or can I just do one column and replicate the results across the other using the scattering rules we got using our group theoretic analysis? Go back and look at those results, and you can use them. There's no need to calculate more scattering parameters than you need to, given the symmetry of the circuit. Or if you're unsure about your answer, you might go through and do two columns. And from the symmetry, if you know that the elements of those two columns should be related to each other by equality, you can then look and see if they are. If they're not, then you've made a mistake somewhere. And so it's also a good way of using symmetry to apply a sanity check.